the live session. Okay, we just wait 1 minute to make sure that we are live. We will be live on a few different platforms, on LinkedIn, on YouTube. Okay, great. Perfect. The session will be obviously recorded, and we will later on upload the recording both on LinkedIn and both on Omdana YouTube page. Let's get started because we already have quite a few people online. I will share my screen, and so. Yeah, guys, so thank you so much for joining. As I said before, please feel free to use the chat to write down questions during the session, because at the end of the session we will select a few of the questions and we will address them in a Q&A format. So the session today is the topic of the session is how to deploy a real-time computer vision model. But let me start first by telling you a little bit of the context and what is Omdana. Omdana is a platform for AI for good. We connect our community of AI engineers with organizations that have impacting missions and that are using artificial intelligence to make a real impact in their work. In 2021, we have incubated in our project incubator 44 impact startups from many different sectors: health tech, ag tech, energy, and many others. And with both Whitbot and Envision it, they have been part of our program in 2021. And they have deployed a computer vision model, and they are going later on to present their case studies. We also, as an organization, we are partner with NGOs. We have worked on impact AI project with many large non-profit organizations like Save the Children, the United Nations Human Refugee Council, and many others. If you want to join Omdana as an engineer, as an AI engineer, you can apply to one of our upcoming projects on our website. You have just to go to omdana.com/projects. We have, I think right now, 5 upcoming projects where you can apply, and you can be selected as one of the AI engineers that is going to work on that project, and that's the way to enter and be part of Omdana community. If instead you are part of an organization, it can be a startup, it can be a non-profit organization, and you want to propose a impacting project on that we could work on to build an AI solution, you can apply via Omdana, work with us, or you can send us an email at contact@omdana.com. Today we will talk about how to deploy a real computer vision model. We will have Aruna, that is an Omdana lead AI engineers, that is going to present first, and then we will have 2 case studies. One from Whitbot. We have the CEO of the company, Janice, and we have the CTO of Envision that is going to share his case study. So yeah, Aruna, you can get started.
Thank you for the introduction, Fabio. I'll share my screen. Can you enable screen sharing, please?
Yes. This is the you should be able to share it.
I'm not able to.
Okay, you should be able now.
Okay. Yes.
Great.
Hello, everyone. I'm Aruna, lead data scientist at Omdina. I'm a software architect and I'm a lead data scientist in NLP and computer vision. Today, I'll walk you through the deployment of real-time computer vision applications. So coming to the topics, computer vision is a field of AI that is used to detect, classify objects, and it has a wider applications like creating 3D maps or motion estimation, autonomous vehicles, etc. Now, when we talk about real-time computer vision, it is where the image processing or the computer vision applications that involve critical time processing. That is, the needs of the application are that the response should be in real time, meaning once the time is lost, the significance of it is not there. So it is mainly used in the control applications where the prediction of the or the control the computer vision applications is used to control certain things, especially in robots, in autonomous vehicles, in smart farming, and various edge AI applications. So these are some of the real-time computer vision applications where it is being used. So one is like biometric access, industrial robots, medical imaging on edge devices. And with the advent of 5G, then there are a lot of edge AI applications. Then recently, like we have seen remote surgery also by NVIDIA. There was a demo in the last GTC. So at Omdina, we have developed some of the real-time computer vision applications. These are some of them. So one of them is detecting of weeds by edge computer vision to reduce the environmental footprint. This is done on a bot. We will get to know of this more in the after this part of the session. Similarly, we have detecting pathologies in ultrasound images on mobile device. So this also has been the inference happens on a mobile device. Then we have application for plant health prediction and drought control. This uses drone data and some IoT sensors. We also have developed an application to help the visually impaired people to use buses comfortably with computer vision. So going further on the topic, so what are the advantages or why do we need this real-time computer vision? So one is the ease of use because we have dedicated devices which are used for this purpose, and it is not really on the cloud. So there's an optimal performance on this dedicated devices, and the workload is distributed between the between the cloud and the edge device. Then it can work in offline mode, so it does not need connectivity. It runs the process by itself. Then you have better response time, also with security and privacy. So these are not like running on the cloud. So these are like working on the edge or the device. So these are better control is there rather than in the cloud. So the downtime is not there. So then how is it different from the regular computer vision? So, and what are the, complexities involved here? So one is the hardware limitations. So this comes with its limitations that it has a lower footprint. The latency has to be low for the application. The power consumption is another requirement here, that it runs at lower powers, and a lesser memory. The hardware capacity is limited, and we have limited connectivity on the edge device. So it is not possible to connect throughout to the cloud. So it added to that, we have complexities in the AML design and the pipeline. So edge inference brings its own challenges and design requirements that need to be considered while designing the neural network and the optimization. So let us dwell on these details a little more. So what was happening earlier was the usual computer vision is all the process happens on the cloud, and the whole thing, like the model is packaged as a service which runs on the cloud, and it interfaces with a REST API. And all the devices like the web application or a mobile device or any other device would interface with a REST API. So it would send an image or some data, and you would get the the result, the prediction or the bounding box parameters or the mask parameters, whatever the model gives are returned in the form of a REST API. And the front end is only the user interface, basically taking the input and showing the input output back to the user, and interface is the rest of the job is done at the cloud. That is the typical process which we use in computer vision. Now we have moved to edge AI, where the inference happens mostly at the edge. So here in this process now, the data pre-processing and training still happens on the cloud, and the inference, once the model is trained and it is converted or optimized that is suitable for the edge device, and we move the inference to the edge. So the application now, the design has to purposefully split the workload and coordinate between the cloud and the edge. Like what is more optimal to be performed on the cloud with more compute resources, which has more compute resources, memory, etc. And then what can be performed at the edge. And we need to rightly balance and leverage the advantage of both the components. So the design of the application, keeping all this in mind, becomes very critical here. So the advantage with Edge AI is, like as we said, it gives immediate decisions, while still the cloud AI can be used for training the new data and also the deeper insights. While the immediate results happen at the edge, the deeper insights or the training with the the new data that is coming at the edge can go back to the training data. So TinyML is one of the concept that has come to bring the cloud-based ML to low-capacity hardware devices. Also, as we said, 5G has opened a lot of possibilities in edge AI applications because of the wireless connectivity to various devices. So when we come to real-time computer vision, till the process of ML model training, the process remains the same. That is, you take the input data, the images or the videos, then you do the regular pre-processing with the libraries, basically collecting, getting the features, feature map and all that. Then you do feature extraction, pre-processing followed by feature extraction, and then you train the model. So which is basically from the feature map that you have done, and you predict and classify the objects. So this process is still done on the cloud, and this remains the same because you still need the compute resources and larger memory for this. Same way, the model metrics also remain the same. Even though it is real-time computer vision, the object detection or the classification, similarly the embedded similarity metrics, all these remain same. The same parameters like precision, recall, F1 score. Similarly, we use IOU for bounding box prediction with confidence score, and you have average precision for each object, and the MAP for the all the objects together, that is the precision of the model. Now you have variations of MAP. These are the regular metrics that we use for the computer vision models. Now coming to the techniques that are needed for converting a model that is suitable for the edge, one of the main techniques that are very important factor is the model compression. So when we train the model on a cloud, it is usually of a larger size. So this would not fit on a low capacity or a lower hardware device that is the edge. So here what we do is we perform certain optimization techniques with minimal loss in accuracy, and the model is compressed, resulting in a faster model and smaller model. The footprint is also reduced. So what are the techniques that are part of model compression? So these are the widely used techniques. One is the pruning. Pruning basically removes the insignificant neurons once the model is trained. So quantization here, what happens is the precision of the weights is lowered. So we will discuss these two in more detail as we have used these techniques in our computer vision, real-time computer vision applications. So the other one is knowledge distillation. Here, the teacher and student models are trained in such a way that the student model, a smaller student model, is arrived with almost the same functionality as the teacher model. So in practice, we use a mix of pruning and quantization to arrive at the optimal model. So if we go to model pruning, this takes care of the reducing the weights by removing the near to zero weights. So most of the weights and all the parameters of the model are stored in floating point float 32 representation or precision. So when it comes to near zero weights, they don't add much value. So these are being removed. This is one of the very easiest techniques to compress the model. So this is one of the widely used technique also. So next comes the model quantization. This is one of the very important topic which is used in model compression. So here, like usually, as we said earlier, all the deep learning libraries store their bytes and variables in float 32 precision. Now, this is when you move it to int 8 precision, there is a clear 4 times reduction in the model size. So you see that the the size of each weight is drastically reduced, and similarly, the memory requirement is also reduced by 4 times, and the speed will go up by 2 to 4 times. This is the observation. So what are the types of quantization that are being used? So one is the static quantization and the dynamic one. And then you have these two are the post training quantizations. And then you have quantization aware training. We will discuss more about these further. So when we say dynamic quantization, here the weights and activations are quantized before computations. Basically, the weights and activations are converted to int 8 precision and then done the computation. So that is how dynamic quantization is done. When you come to static, you need a calibrated data set. We do the same thing, but with a calibrated training data set to achieve an optimal quantization. This is more precise than the dynamic one. Also, like you will know like which is more suitable for this data set. So the next comes the quantization aware training. Here, this process is happening during the training itself, whereas the dynamic and the static ones happen post training. Quantization aware training happens during the training process. So what happens here is that the float values are rounded to the int values while computing, but the computation still happens in the float. So the model takes care or the this process takes care that you get the best values of int 8 precision. So the weights are adjusted in such a way that the process knows that the model is going to get quantized as in the next step, thereby yielding a higher accuracy. If you want to know the highest accuracy out of all this, QAT gives the highest accuracy because of the process involved here. So now we will go into each of the mobile device deployment and the other edge case deployments. So when you make a PyTorch model and we want to deploy to an Android device, the process is like you convert it into a torch script, which is used for serialization, and then you do further optimization with further optimization is performed with the with the torch script itself, and then it is converted and saved into the mobile. So here is the process that shows the same thing. Similarly, if we develop the model based on TensorFlow, so TensorFlow Lite is being used here. The same process is being followed, where the model is converted to flat buffers, and it is deployed on mobile, IoT, and Raspberry Pi devices. So the data here shows that the when you do QAT, the almost very less difference is there in the accuracy, very minimal effect. So the components of TensorFlow Lite are the converter and interpreter. So converter shrinks the model, and interpreter is run on the in a mobile device during the inference time. So similarly, there are certain edge optimization techniques. These are some of the libraries that are being used. If we go with NVIDIA devices, we have certain libraries that are specifically for this purpose of optimization, based on because these have the GPU devices on the hardware. So these libraries are provided for optimal use. So we get the best results when GPUs are most used. So we have QDNN, which is part of the CUDA SDK from NVIDIA, which uses which can be leveraged for developing the CNN. Our CNNs can be written using QDNN. So similarly, OpenCV has this OpenCV DNN library, which is optimized for GPU. And TensorRT is used for quantization. And these two, the PyTorch and TensorFlow libraries, which are used for mobile devices. The models can use this Torch script and TensorFlow Lite to convert the model and optimize for mobile devices. So the optimization techniques that we have performed on NVIDIA Edge devices is the model is trained and on the cloud, and it is converted to ONNX format. ONNX is standard format which can be converted by across the libraries like TensorFlow or PyTorch, any of those. So ONNX is the standard format, and that is passed to TensorRT library to generate the int8 precision model. So the other optimization techniques that we did was using OpenCV C++ library for image processing. Now, if you see, OpenCV Python is a wrapper on OpenCV C++ library. So directly OpenCV C++ library is used for, to get better latency during image processing. Then using QPy. Another experiment was to use the lighter backbone, such as MobileNet and other frameworks that we will see down the line, which are those frameworks that we have used. And then another experiment is the precision of the images can be reduced to get higher latency. So this can be a trade-off, latency versus precision. It depends on the application that we are going to use. If the application uses more of contour kind of a image processing, and if the prediction is based on that, then it does not need a high precision image. It does not affect the accuracy so much. So in such cases, we can go for lower precision. So again, these are all the experiments that we need to do, and what best suits for the hardware and for the given data. These are the experiments that need to be conducted. So coming to the challenges that we faced, or the usual challenges that we face in real-time computer vision application, is that one of the critical thing is to identify the right hardware for the given application. So it depends on aspects such as do you need a GPU? Will you need what kind of application is it? If you're is the latency time latency time, memory requirements, and things like that. Based on this, you determine what kind of a device or hardware you would need. Similarly, like what is the device or the OS and its libraries that you're going to use on the hardware. Apart from that, the impact, the other aspects are the which are concerned with the ML process, are the data ingestion, the pre-processing, the annotation pipeline. These have to be designed in sync with the keeping in mind the deployment process. So the other aspect is the deployment of the model to edge post training. This also has to be planned accordingly. Another aspect is the very key important aspect is the model optimization. What kind of a series of experiments need to be done regarding the to get the right model, sorry, optimization on the particular hardware, and what kind of latency is desired, whether you can trade off with latency precision. These are the experiments that we need to do. Similarly, the size of the model, a lot of benchmarking experiments are needed, and of course we need the DevOps and the edge device expertise is needed. It's a mix of all these components to make a right real-time computer vision application. So some of the best practices which we have observed during when we have developed these applications is that the first aspect is you understand the constraints of the device and accordingly design the application. Because all these factors you need to consider right from when you design the data pipeline or the deployment pipeline or the experiments, allocating the right amount of resources and the expertise also makes a big factor. So also you need to design the flow of training and model deployment to edge device. So the libraries for model optimization, image processing, these you have to be aware of. Similarly, you need to write the code optimization plays a big factor because if it is a generic computer vision application, these factors are not so significant that to get a smaller footprint, to be a faster, to get faster inference, it is not that significant whether it is 10 milliseconds faster or slower. But whereas here it matters, because as we said, these are like, if you see the controls, once you pass that time, the significance of that has lost. So there is no use of that prediction. So it's very important for the real-time computer vision application to take into account these constraints. So also using tools for profiling, like NVIDIA provides certain tools for providing the GPU usage and memory usage. So these are the important things that are needed for an optimal usage on the device to design and get a good application, real-time CV application. Similarly, we have to study the latency versus precision trade-off. What is the impact and where you want to compromise, and which is the part that is okay. Then we have the lighter backbones help in making it a lighter network, like for example YOLO v4 Tiny, SSD MobileNet v2, and YOLAC Edge. We have also we need to allocate some time and resources for benchmarking experiments. Another factor is with respect to data, like you have to take into account the class imbalance, augmentation. Sometimes the data is not available, so you have to go for synthetic data. So DevOps expertise also is needed. Real-time computer vision is a mix of data science, DevOps, embedded systems. It's a mix of all these expertise together. And mobile app development in case the application is going to run on a mobile device. Familiarity with all this will help making a good application. So this is the I'm going through the slides which we have done at Omdena for some of the applications. So this is a deployment flow. So we have for the data is being managed at the cloud. So the trained model and the data are in the cloud. The quantized model is taken, dockerized into a container, and it is deployed. After the quantization and optimization, it is deployed on a mobile device. So this is one of the application which shows the mobile device being used for visual impaired people to use the buses through computer vision. So this is the application that is being developed with TensorFlow Lite, and you can see the the object classification of the bus panel. Similarly, empty seats, which is going to help the person to go to the right bus and to get into the empty seat. This is a diagnosis that happens on the mobile. This is one of the applications. We are going to have the detailed case study on this further down the session. So this is where some image processing has happened, and then the model is being deployed on a mobile device. So as we discussed here, like Omdena has developed some of the impactful projects in this area of real-time computer vision, and our partners are going to share more details about the applications on this. I'll pass on to you, Fabio.
Yes, thank you so much, Aruna, for the presentation. So now I will give the floor to Yanis, CEO of Wheatbot. They were part of the Modena program last year, and they developed a very amazing real-time computer vision model. So Yanis.
Hi. Thanks a lot for the floor. Happy to be here. Yeah, it was a pleasure to work together with the Omdena team and also Aruna. So happy to be here. I will give a broader view of this, as I'm not myself a developer or software engineer, but I think yeah, I will give some more general advice from my perspective, what things should be taken care of while developing something on the edge device. But I will start with some overview of how our product looks like, just to give an intro for listeners. So Fabio, can you give me the sharing rate?
Yes, sure. Just one moment. Okay. Yeah, you should have them now.
Okay, let's try. Not yet.
Okay, I found a way. Yes. So you should be able to do it now.
Yep, now it's on. Okay, good. I will put a short video just to show how our use case of edge computing looks like. So we are a company that develops tools for farmers. So we have developed high precision weeding tool that can recognize weeds and treat them with laser. Our machinery is attached to the tractor, so it can be easily integrated in existing growing system of the farmer. We are using blue lasers for this purpose, and compared to manual work, our system can work both day and night, so a lot more time on the field. So I'll put a small pause here. So this is how our recognition part looks like. We use both neural networks and other computer vision bits and pieces to make everything work smoothly. At this moment, this image is about carrot recognition. So you can see with a green carrots that has been recognized, and with red there is weeds in the images. So we are processing it real time, and this is in a bit of slow motion. There are a lot of images per second that need to be calculated and treated. And when this recognition part is done, then our laser takes his part, and we treat all green parts of the weeds with a laser. Okay, that's from sharing part. So yeah, in general, a lot of what Aruna was talking about is something that we have gone through. And just to give a more perspective, what our hardware setup looks like. So as in the video, we are taking image from the top of the row. We are putting these images through edge computing device, separating good crops from the weed crops, calculating the exact coordinates of our plants, and then shooting with a laser to these coordinates of the weeds. And in theory, it sounds quite simple. Take image, calculate, and then treat with laser. But it's it's a lot of steps in between. And the three main things that I wanted to emphasize today is regarding choosing the right neural network or CV2, putting hardware and software in the right harmony, and think more about expectations and then the real life situations. So regarding the choosing the right tools, the right network or vision tools, in our case, we have worked with different models, starting from YOLO, RCNN, YOLACT, BallNet, and others. And the main reason I'm mentioning is that not always the best or the best references, the tool that has best references is the right for you. So I would strongly suggest to test several of them and then choose the one which gives you the right or expected results. As in our case, there are often willingness from the developer to use something which is more simple or more maybe faster to be implemented. And this is a way how it seems like it would be the right choice. I would strongly suggest to evaluate all options, because time that you spend improving something which cannot be improved will be much more compared to what you will spend at the beginning choosing the right tool. The second aspect, which is also quite important, is putting together hardware and software, which was especially in our case, as we are looking at plants at very high resolution. We are using high resolution camera, and also images that we are putting through the neural network. It is much higher resolution compared to usual recognized cat in image or recognized face in image, where much lower resolution is acceptable. So in our case, when we get the initial results from the model that it works, then we started to put it together with our hardware part. And by hardware, there is the part which takes images, the camera. We have a computing unit, either a computer-based or chip-based, and then we have mechanisms that are executing something. In our case, these are lasers, and all of them have different limitations and different formats how they are expecting information to get in them, and also specific formats how the information goes out of them. And again, the neural network or other recognition softwares are very limited in their use if they are not directly connected with these other peripheral devices. And this is important next step. How well are they communicating with each other? And in our case that we observed that you can lose a lot of time if the communications between is not the right way. And just clearly, just from the computing unit perspective, again, when we are talking about edge computing and edge device, then from one point we would like to have less costly and smaller units. On the other side, there is computing power of them. And again, in our case, we need quite a lot of computing power, and there needs to be some compromise. How much are you willing to spend for the computing device, and what is the speed afterwards, what you get from the neural network and other software components. And this is very important, especially in those cases when the size is a factor. For example, for the drones, we have our colleagues working on a drone area, and for them, it's really complicated to put something heavy on the drone. And for that, you essentially then cannot use very heavy weighted neural networks just because your edge device is not able to compute such a large amount of information. And the third aspect I wanted to emphasize is regarding the expectations and what you get at the end. And it's quite easy to put very high expectations and put the speed limits, resolution limits and something beforehand. But the real life hits you quite hard often. And I would also say for everybody just to be prepared for that and put your limits what you would like to achieve, like the best scores, then put some medium and also the lower, below which you would not like to go, because at some point, yeah, you will need to make hard compromise. And the sooner you put these limits on, the easier is the choosing the right, both the hardware and the software, just to be on the right, to get the right balance. Because I really wouldn't be in situation when you have spent a lot of time, but at the end, you cannot use the result of your computer vision system just because there was too many compromise between hardware, software, or other issues, and at the end, it's either resolution or the speed is not there. So yeah, we need to be prepared.
I think your case study is really amazing. I am a little bit concerned with time because we have also Envision it case study. I would like to ask you just a quick question, if you can reply shortly. If you can tell me what was the biggest technical difficulties that you had before joining Omdana incubator program, and how that was solved during the project.
Yeah, we joined Omdana with the speed limitations, as we have quite heavy network. And yeah, during these 8 weeks, we and the Omdana team worked hard to get some ways how we can overcome these speed limitations. We get good leads there. We didn't get in these 8 weeks because it's quite short time period to exact solutions for that. But yeah, we definitely get some good leads which were used afterwards to get our network as it need to be working on the edge device.
Thank you so much, Yanis. Now I will give the floor to Andrei. He's the CTO of Envision It, an amazing South African or African-based health tech startup that will present us his case study.
Thank you, Fabio, and thank you to Mdena for inviting us for inviting me to speak to you, to everybody. Fabio, I'd like to share the screen as well. So whatever you've done previously,
Yes.
Can you do that again?
Now I did it. I did learn from my mistakes. So you should be able
Still
to
can't
share your
share.
screen already. You can't?
Nope.
Let's see. Okay. Now let's try now.
Perfect. Thank you.
Great.
Okay, I'm going to do a couple of slides just to talk about Envision the Deep AI. What do we do? They need for real-time processing or near real-time processing in some cases, why it is important. So first of all, to start off, my name is Andrei Megachev. I'm one of the founders and the CTO of Envision a Deep AI. We've created a number of different platforms, but today I will be talking about the Redify platform, which is a platform that uses artificial intelligence in radiology images. So medical imaging, but specifically X-rays, ultrasound, and going into CT, MRI, and other modalities. So at the moment, a Redify platform is designed and capable of detecting numerous different pathologies on a chest X-ray, on a mammogram, on ultrasound images, as well as a video stream, highlight them on the images or a video stream, as well as has a capability of predicting or suggesting what exactly those pathologies mean in the context. We have a number of different product offerings within the Redify platform, specifically Redify platform for COVID, pneumonia, a Redify platform for tuberculosis, a general Redify platform for chest X-ray, for mammography, as well as for ultrasound. Now, all of these different products, they share the same main trait of the ability to detect or infer certain pathologies on the image and provide a conclusion to this in 20 milliseconds. So we are looking at real-time to near real-time performance here. In a lot of cases, a patient wouldn't even get to pick up their shirt to put it back on after an X-ray, and our AI models already provided the first pass or the first reading and provided their predictions. Also, one of the interesting aspects, and this is something Aruna was talking about, is it is very important to understand your deployment. And from the beginning, we were looking for an ability not only to deploy in a very well-developed metropolis, like Johannesburg or London, with very good connectivity, availability of resources, power, but are also going into rural and remote areas in Africa, South Africa and Africa, where connectivity to the internet is a premium, power is a premium as well. There are a lot of power interruptions, so ability to run on a UPS and a significantly less than a normal power consumption is very, very important. So our Redify platform can be used as a standalone unit connected directly to one or more modalities. Typical applications to this are mobile X-ray units. Specifically in the COVID pandemic, we've seen it where tents or units were set up outside of major hospitals where people could come and screen themselves. Mobile units that are mounted on inside vans or trucks and can be transported from one area to another. Again, in the COVID pandemic, we've seen a lot of usage of those. As well as occupational screening employs such mobile units as well, where the response of the model and the ability to provide prediction as fast as possible is very, very important. A lot of the times you don't have a radiologist that is there and capable to view the image right away. And if there is a technical issue with the image that was taken, and our model is immediately identifies this, a radiographer is capable of taking another image and make sure that the second image is as crisp, clear as it should be, for reading by the radiologist. But we also are capable of running in a connected environment integrated into a hospital or practice systems into the internal networks, communicating with the variety of different hospital systems such as PACS or RIS. PACS is an archiving and a communication system for radiology images, and RIS is the radiology information system. So from the workflow perspective, and just to show you the difference that our system provides in a setting, I've got two flows on the right side of the slide that demonstrate processing or a typical workflow with and without the AI, and the improvement in speed, accuracy, error detection, which can be done very, very fast, and a corrective action can be taken in taking a secondary or a third image with a video stream with an ultrasound device where we can highlight areas of interest in the video stream that is displayed to the radiographer. As the radiographer is moving the ultrasound probe, we can highlight the areas that the radiographer should be concentrating on, providing immediate feedback, which makes for accuracy, decisioning support, and time efficiency. This is just a couple of quick screenshots of what the Redify platform provides. You can see the regional image, you can see the augmented image, where we would provide or highlight the areas of interest, where specific pathologies were detected, provide the conclusion of what we believe or AI believes that these pathologies mean, generate the heat maps, and all of this is done in a matter of milliseconds, not even seconds. Most of the time we've seen the latency on the network being slower, or that latency being longer than what it takes the AI models to process the images and provide the output. Thank you very much. Any questions, Fabio? Anything else that you would like me to mention or talk about?
Yes, I will make you the same question I made to Yanis before. So yeah, if you can tell us from computer vision technical point of view, what were your biggest difficulties before joining the Omdana incubator, and how the 50 AI engineers that work on that project address that issue?
Well, I think that the most important part about working with Mdene, and something that we truly enjoyed, is the ability to share knowledge, information, experience, and work together with a large pool of resources, large pool of data scientists from different industries, from different expertise, with varied experience in the field. Sometimes, just because you're coming from a completely different background and different computer vision applications, some of the things that were done or used in that particular environment and those particular projects, could be interested in other aspects, that are not immediately visible. Like they normally say, a fresh set of eyes is, good to look at a problem. And it was really a pleasure working with a Mdene data scientist and sharing ideas and concepts and creating the prototype that we've created together in those 8 weeks. There's still a lot of work that needs to go into 8 weeks. It does sound like a lot of time, but in reality, it is very, very quick project. But an ability to work with so many different resources from different walks of life definitely benefited us in creating the prototype that we needed to take some of our solutions or some of our offerings and ideas into more concrete products.
Great. Thank you so much, Andrei. So we had quite a few questions, both on the question and answer section and in the chat. We did reply already to a few of them in the chat. Aruna, there is some particularly interesting question that you would like to address live quickly before to close the...
Yes, Fabio. I have a few interesting questions here. So one of the question is on, actually 2 of the questions are on model pruning. How do we go about pruning? How do you identify the 0 or near 0 weights once a model is trained? So once the model is trained, we can save the weights, the pickle file or whatever format, and that can be, the library calls are there for pruning. So you can give a threshold value and say that beyond below this value, like the weights can be discarded. So these are not really helpful for the model accuracy. These are like dummy kind of weights, like near 0 or insignificant weights. So that way the pruning works. I have another question. I think this with respect to wheat bot. So does the model only work with carrot leaves and beets or any other plants like carrots, like potato, onions, etc.? Yes, the model would work for any of these classes. The main task is in the data annotation. So we use the CVAT tool, or we can use any other annotation tool like label box to identify these different classes which you want to train the model for, and it can be used to distinguish any of these leaves or the carrots from or these objects, basically the potatoes or onions.
Great, thank you so much, Aruna. So thank you to everybody that took part to this event, especially to Aruna, that is an Mdene lead engineer, to Andrei, who is the CTO of Envision, and Yanis, who is the CEO of Wheatbot. As I think you saw, like real-time computer vision deployment is not easy, and it takes a lot of effort and a lot of knowledge to do it properly, to do it in a production and at scale. We see that there are a lot of startups struggling with it. So if you are a startup and you have an impacting project and you want to develop and to deploy your computer vision model, you can get back to us, to Omdana, and we can take into consideration your project for our next batch of startups. And if you are an AI engineer interested in computer vision that wants to put your skill in a real world impacting project, feel free to join to apply for one of our upcoming projects. And I hope it was interesting for all of you. And thank you again, everybody, for joining this session. Bye.
Thank you very much. Cheers.
Thank you.
Thank
Bye-bye.
you, everyone. Bye.